Thanks, Bernhard, for the invitation to this seminar. It is my pleasure to speak here. So today I'm going to talk about some new rigidity results for initial data set satisfying the dominant energy condition. And these are based on a joint work with Professor Baer, Professor Brendle, and Professor Hanke. So this is the outline of my talk today. So I will first introduce some history of initial data set rigidity. And then in the first part of my talk, I will discuss rigidity for smooth manifold with boundary. In the second part, I will discuss rigidity result for convex polytope. Okay, so let me begin. Okay, so let me begin by motivating why should we consider initial data sets. So an initial data set, so it first arises from general relativity as a snapshot of the space-time at a single moment in time. So mathematically speaking, in general relativity, the space-time is modeled by a Lorentzian manifold with dimension, time dimension n and space dimension n and time dimension 1. And a snapshot is represented by a space-like hypersurface in the Lorentzian ambient manifold with induced Riemannian metric from the ambient manifold and induced second fundamental form, which I denote it to be Q. And on the other hand, we can also study when does a Riemannian manifold can represent a snapshot of the space-time and the evolution of that space-time with the given Riemannian manifold being the initial data. So this is like the Cauchy problem in general relativity. So this motivates the concept of the initial data set. So the definition for an initial data set is a triple MGQ, such that M is a Riemannian manifold, G is a Riemannian metric on M, and Q is a symmetric CO2 tensor on M. So later, we would like Q to represent the ambient second fundamental form if M is embedded into a Lorentzian manifold. So for a different initial data set, so if we want this initial data set to represent a space-like hypersurface with a future pointing unit normal factor E log in a Lorentzian manifold N, which satisfies the Einstein equation, then this data must satisfy this so-called compatibility equation. So basically here, this is the Einstein equation introduced by Einstein. And on the right-hand side of the equation, this is called the energy momentum stress tensor coming from physics. So in general, the component of T looks like this. So here mu is called the local energy density. And here J is called the local current density in physics. Okay, and if M is a space-like hypersurface in the Lorentzian manifold N, then by restricting the ambient metric on M, which gives us the Riemannian, so which is G, then by the Gauss and Kodály equation, we can derive these two equations from the Einstein equation. Okay, and for physical reasons, we need mu and the data mu and J to satisfy the so-called dominant energy condition. So which says that mu minus the norm of the local current density J has to be non-negative. So this is for purely physical reasons. Okay, now so let me introduce some history of initial data set rigidity. Right. So again, this comes from motivation from general relativity. So in short, in general relativity, so graph of T is represented by curvature of space-time. And basically, the Einstein equation tells you that matter will affect how the curvature behave in the manifold. So in physics, physicists expect that the Minkowski spacetime, so which is the spacetime without any curvature, that means without any gravity. So physicists expect the Minkowski spacetime to be the only zero energy state. That means when the spacetime does not have any matter, we would like such a spacetime to be gravity free. So that is Minkowski spacetime. And basically, this translates to the rigidity of rigidity statement in the positive energy theorem. So let me introduce the positive mass theorem, which was proved by Yao and also by written independently. So consider an asymptotically flat initial data set satisfying the dominant energy condition, and let E to be the total energy of the space of the initial data set. So which is the ADM mass. So the formula for E are divided on N of the manifold would look like this. So it is let the integral of some data coming from the metric taken over a sphere of very large radius, and then we take the radius to send the radius to infinity. So this is the notion of the ADM mass. And the positive mass theorem asserts that the ADM mass has to be non-negative. Okay, so this was proved by Yao and Witten in either dimension less than 7 or when the manifold is spin. And so today I would like to focus on the rigidity statement. So the rigidity statement says that when the energy is 0, so this can happen if and only if the initial data set M can be isometrically embedded into the Minkowski spacetime, with Q being the second fundamental form. So basically the rigidity statement is a mathematical way of saying this expectation from physicists. Right. So this seminar is about scalar curvature. So at this point, let me point out the relation of initial data set with dominant energy condition with positive scalar curvature. So we call that a few slides ago. So we call that the dominant energy condition mu. So mu is given by this expression, and J is given by this expression. In particular, if we take Q to be 0, then mu is simply 1/2 times the scalar curvature of the manifold, and J will become 0. So this means that when we take Q to be 0, then the dominant energy condition is actually the same as non-negativity of scalar curvature. Okay, so when Q equals to 0, this is also called a time symmetric K, but that means there's no curvature in the time direction. And in this case, the dominant energy condition reduces to the PSC condition, and there is a corresponding Riemannian version of the positive mass theorem, which was also proved by Yao and Witten. So the Riemannian GMT says that if Mg is an asymptotically flat manifold with non-negative scalar curvature, then the ADM mass of the manifold is non-negative, and when the ADM and energy can be 0 if and only if the manifold is flat. So it is the flat Rn. Okay, and let me also point out that the Riemannian positive mass theorem is also closely related to the Gerber conjecture. So the Gerber conjecture says that on a torus with a Riemannian metric satisfying scalar non-negative, then this metric has to be the flat metric. And moreover, on a torus that admits no metric with positive scalar curvature. So you can think that this is like a prototype of the positive mass theorem. And this was proved by Yao and Gromov-Lawson. Okay. So going back to the Riemannian positive mass theorem, for the rigidity statement in PMT, it can also be used to imply the following corollary. So basically, it means that it says that there exists no metric on Rn such that it has positive scalar curvature in a bounded region. So that means on Rn, there is no local perturbation of metric which can increase scalar curvature. So this is also a consequence of the Riemannian PMT. And the reason is that the energy stays zero under any local perturbation. And then, but the rigidity statement then implies that M has to be flat. Okay. So far, there are two main approaches to tackle this type of rigidity problems concerning positive scalar curvature or initial data set satisfying the dominant energy condition. So the first approach is to use minimal surface technique and slicing. So this approach was adopted by Shen and Yao in their proof of the positive mass theorem and the Dirac conjecture. And the second approach involved the use of spin geometry and the Dirac operator method. So this approach was adopted by Gromov-Lawson in the proof of Dirac conjecture and by Witten in his proof of the positive mass theorem. Okay. So in this talk, I will focus on the Dirac operator method. So let me give you a rough idea of how to use the Dirac operator method in general. So the first step is to use the topology of the problem to construct long-trivial solution to the Dirac equation. So for example, in the proof of positive mass theorem, Witten used Fredholm theory and asymptotically flatness to construct a non-trivial solution to the Dirac equation. So you can either use like Fredholm theory, or another way, you can use index theory to construct non-trivial solution to the Dirac equation. So which appears in Gromov-Lawson's proof. And okay. And here S is a spinor, which is a section of the spinor bundle, and D is the Dirac operator. Okay, so having construct a non-trivial solution to the Dirac equation, the second step is to use this Weissenberg formula concerning the Dirac operator to derive integral estimates. So this Weissenberg formula gives you some very close relation between the Dirac operator and scalar curvature of the manifold. Okay. So perhaps let me illustrate such idea using an example. So let me use this lower-Ridge theorem as an example. Okay, so this theorem says that when the dimension is 4K, then PSC will imply vanishing of A hat genus. So the idea is like this. So suppose the A hat genus of the manifold is non-zero. So this is like a topology condition. Then we can apply the Atiyah single index theorem, which tells you that the A hat genus is the index of the Dirac operator. And when the A hat genus is non-zero, then we can use the Atiyah single index theorem to construct a non-trivial solution to the Dirac equation. And in the second step, we integrate the Weissenberg formula, so which gives us the following integral. Okay. So the left-hand side is 0, and the right-hand side is positive by the assumption of having PSC. So this gives you a contradiction. And so this implies that the A hat genus cannot be non-zero. Okay, so this is like a rough idea of how to apply the Dirac operator method, improving theorem of this kind. Okay, so now let me go back to say a few words on Witten's idea on his proof of the positive mass theorem. So, firstly, using the assumption that the initial data set is asymptotically flat, Witten was able to construct a non-trivial solution to the twist or perturbed Dirac equation. Okay, so the rigorous statement for this step is given by Parker and Taubes. Okay, and a solution is also constructed in a appropriate weighted Holder space. And the second step, Witten observed that by integrating over this Weissenberg identity, this integral is bounded above by the energy of the ADM energy of the manifold. Okay, so on the left hand side, this is 0. This term is 0 because S is a solution to the Dirac equation. This term is non-negative, and by assumption of the dominant energy condition, this is a good term. So this will force. So in particular, this means that the energy is non-negative. And for rigidity, when the energy is 0, then this will force this term to be 0. So that means we obtain parallel spinor. Okay, and this existence of parallel spinor will then be used to construct a isometric immersion into the Minkowski space. Okay. Okay. So now let me move to the rigidity the rigidity results for initial data set for manifold with boundary that I want to discuss today. Okay. So now the motivation is to formulate conditions which ensure that a given initial data set associated with a compact smooth manifold with boundary is a space-like hypersurface in the Minkowski space. Okay, so in the positive mass theorem, we are concerning with a complete manifold, a complete asymptotically flat manifold. And now I would like to consider the case of compact smooth manifold with boundary. And we will consider the following class of manifold with boundary. So let K be a compact convex subset in Rn with long-empty interior. And let the boundary of K to be smooth, and let capital N to be the exterior normal of the set K. So because of convexity, the map N will have degree +1. And now let's consider a map F from K to R which satisfy these two relations. So later, we would like to consider the graph of F in the Minkowski space. And the first condition will ensure that such a graph is space-like. This will ensure that graph is space-like. Right. So now let's consider a manifold which is defined to be a graph of F inside the Minkowski space. So this is a graph over a compact convex subset in Rn. Okay, and so this graph is a compact smooth space-like hypersurface with a boundary lying in Rn. Okay, so now if we denote, okay, so here we are considering graph of F of a function F over a convex subset. Okay, so now suppose let's denote capital T to be the future-oriented normal vector field of the graph M in the Minkowski space, and let G be the induced Riemannian metric on M, and Q be the induced second fundamental form on M with respect to T. So this will mean that Q here, Q of xy will be the inner border of dxt and y with respect to the Minkowski metric. Okay, then you can check that under this notation, following conditions are satisfied on this graph M. So firstly, because it lies inside the Minkowski space-time, mu minus j will be identically 0. And secondly, the mean curvature equals to the trace of Q restricted to, on the boundary sigma, plus the trace norm. This is the trace norm of the linear map Dn. So which is defined to be the sums of all singular values. And here H is the mean curvature of the boundary surface sigma in the manifold M. So it is not the mean curvature of sigma in the Minkowski space-time, but it is the mean curvature of sigma in M only. Okay, so this shows a illustration for how this graph would look like. Okay. So our first result identify this class of example as an extremal case of initial data sets. Okay. So suppose MGQ is an initial data set such that M is a compact connected B manifold with smooth boundary, and let M be a smooth map with positive degree. So we assume that the dominant energy condition holds in M, and we assume that H is bounded below by the trace of Q restricted on sigma plus the trace norm of Dn. So we assume this holds to we assume that this holds along the boundary of M. Then under these assumptions, under these three assumptions, then the manifold Mg is isometric to a manifold appearing in this example. Okay. Then as long as we have these three conditions hold for this initial data set, then it must be such an example. So it must be a graph over a convex subset in Rn. Okay, such that Q is the second fundamental form of M in the Minkowski space, and such that the map N agree with the exterior normal of the compact convex subset K. Okay. Then moreover, if we take Q to be 0 in this theorem, then we have the following corollary concerning rigidity of positive scalar curvature. So this says that if Mg is a compact Riemannian B manifold with long empty smooth boundary, and N is a smooth map on the boundary to Sn minus 1. Okay, then if the manifold has non-negative scalar curvature holds in the interior of the manifold, and on the boundary of the manifold, the mean curvature is bounded below by the Chase norm of Dn, and n has positive degree, then M can be isometrically embedded into Rn as a compact convex subset. Okay, so this means that M is a convex subset in Rn, such that N is the exterior normal of M. Okay, so now let me give you the idea of how to prove this theorem. So we will separate the proof in odd dimensions with even dimensions. So in the first step, we will study a boundary value problem for Dirac operator on a twistor bundle. So let S be the spinor bundle over M with respect to the metric G, and let S log be the spinor bundle over Rn. Then we consider the bundle E to be defined by S twisted by S log star. So S log star is the dual of S log. Then for any section in this complex vector bundle, we consider the following initial value boundary value problem. So S solve a perturbed Dirac equation in the interior of M. And on the boundary, S satisfies a chiral boundary condition. So if we define chi by this map, then you can check that chi square is the identity map, and chi is self-adjoint. And this will be a chiral boundary condition. In the sense of Bayer and Baumann. And it is also an elliptic boundary condition. For this first order PDE. Okay. And let me also say a few words about this twisted bundle. So if we look at the fiber of the bundle E over M over a point in M, then this fiber over the point is the fiber of the spinor bundle S twisted with S log star. But this is the same as the homomorphism group of S log to the fiber of S on X. Okay. Okay, so we consider this initial boundary value problem. Okay, and then to solve this boundary value problem, we apply the Atiyah-Sanger index theorem together with the holographic index theorem proved in the work of Bayer, Brendle, Hanke, and Wang in last year. And then we find that the index of the Dirac operator, or the index of this boundary value problem, equals to the degree of the boundary map N. Okay, so this identity, the holographic index theorem is applied, and on this identity, Atiyah-Sanger index theorem is applied. So in particular, in our assumption, the degree of N is positive. So then, by the index theorem, if the degree of N is positive, we can obtain a long-trivial solution to this boundary value problem. Okay. So having constructed a non-trivial solution to the boundary value problem, the next step is to study the Weissenberg identity. So in particular, if we integrate over the Weissenberg identity, we obtain this integral estimate. Okay. So in this integral estimate, you can see that this term is zero because S is a solution to the Dirac equation. These two terms are positive, non-negative, so they are good terms. And by another assumption on the boundary, this term is non-positive, so which is also a good term. Okay, so this integral estimate together with the assumption of the theorem will force this term to be zero. So this implies that there exists a parallel section S, and so the existence of this parallel section will eventually be used to construct a local isometric immersion into the Minkowski space. So basically, we also have the boundary condition being satisfied by S. So if we also explore the boundary condition, it will imply that the section S is invertible. And basically, this will give us a basis of linearly independent spinors. So it will give us a basis of parallel spinor, which can be used to construct the local isometric immersion into the Minkowski space. Okay. So this concludes the proof in odd dimensions. In even dimensions, there is some extra technicality. The reason is that when a dimension is even, we cannot apply the index theorem directly. So in even dimension, we will consider a manifold M tilde by crossing M with a S1 factor. And we equip this manifold with a metric G tilde to be G plus R squared dt squared. So here R will be a parameter which will be chosen sufficiently large later. And then we can find a smooth map from S M-1 cos S1 to Sn, such that the map N tilde, which is defined by the composition of phi with the map N. Then N tilde is a boundary map from the boundary of M tilde to Sn. And we can find this map phi such that the degree of N tilde agree with the degree of N, and such that the trace norm of dN tilde is not much larger than the trace norm of dN. Okay. Okay, so in this case, okay, so now by assumption, we will have the degree of N tilde is also positive. So we can apply the same argument as in the proof for odd dimensions. So for each R, we can find an element in S1 and along trivial section S over the manifold M, such that this integral estimate holds. So so we have an HR term here coming from this this product. Okay. But eventually, what we are going to do is we can take out a sequence of R and send this sequence to infinity so that we can kill this extra bad term. Okay. So we can take a sequence R to infinity, and by passing to a subsequence if necessary, we can find a limiting section which satisfies this good integral estimates as before. And again, the assumption implies that the right-hand side is non-positive. So that will force this term to be zero. And so we can find a parallel sections RS, and this can be used to construct a isometric immersion into the Minkowski space. Okay. So next, let me move on to discuss rigidity results for convex polytopes. Okay. So now so in this
question first.
yes, sure. Yeah. Let me pause for questions in the previous session.
Christina, we can't hear you.
I'm saying we should pause for questions.
Okay.
Yeah.
Any questions?
I mean, maybe remark. So in the main theorem, it is not assumed that the boundary is connected. Right. So, I mean, it's
Right.
you didn't write it,
Right.
but just to make this clear. And in particular, we need beside the isometric embedding into Minkowski spacetime to make sure, for example, that the boundary components are all mapped to hyperplanes. Right. So, and this is something that for this, an additional argument is needed.
Right.
It does not directly follow from what we've seen so far.
Right. Yeah. So I didn't provide argument for this part, but this is also a very important part of the main theorem. Yeah. And so here the boundary can be is not assumed to be connected. So if the boundary is not connected, then basically then the degree of n will be the sum of the degree of the boundary map on each boundary component, and then the argument can still proceed.
But of course, it is part of the conclusion that the boundary must be connected. So in the end, it is connected.
Yeah. Thanks for the comment.
And it's mapped to a hyperplane.
Right. Yeah. So that will coincide with this picture.
Yeah.
What about a region? What about a region where it comes around and overlaps itself?
Yeah.
Yeah. So in this case, I think what we can prove is, so we can prove that the region is exactly a compact convex subset. Okay. I think it is also a embedding, I think. Yeah, so this should be able to rule out the possibility of overlapping.
Right. So Christina, this is also part of the conclusion that this cannot happen. So one embeds in isometrically into Minkowski space, and then one has to prove that the projection onto a hyperplane gives still an injective embedding onto a convex subset K. This is kind of one step in the proof later on.
Excellent.
Right. Yeah, so the picture
And
is
the boundary
very
can't overlap either.
Right. This is all
Very
these
nice.
are not
Okay,
possible.
interesting.
Yeah.
Thank you.
Yes. Yeah, so the picture is quite rigid. So basically it looks like this. The boundary is a boundary of a convex subset on hyperplane. And then the manifold M is given by a graph over this convex subset.
Yes.
But to just clarify Christina's comment, so from the theorem on the next slide, and if you consider such a overlapping kind of snake eating itself kind of picture, we should conclude that there is no map n so that condition 2 is satisfied for such a initial data set.
Yeah, I think that will also be a consequence of this rigidity statement.
But I mean, there are these examples of initial data sets that are flat, but not only locally flat, but not globally embedded. And so I guess since the conclusion can't include those, then condition 2 must fail.
Right. So here condition 2 is actually quite rigid. So it is not satisfied by any space-like hypersurface with boundary. But this imposes a very strong topological conclusion, restriction on the manifold.
Can I maybe ask a really naive question, but I'm just trying to wrap my head around this condition too. It's somehow meant to be like a condition that like some mass is non-positive. Is that correct? Or
I did so. It didn't think it's in this way, but I think yeah. So like if you want to relate it with like quasi-local math, usually we will express this condition in terms of integral of the mean curvature. But here we are using a pointwise condition here. So it is kind of related, but not exactly the same.
okay. Right. Is there a good way to sort of think about it in this kind of mass picture though? Like you want to say sort of the mass is 0, so therefore it's in flat space, right? Or am I?
Yeah.
So I'm
yeah.
sort of
So yeah, but that's
okay.
right. Yeah.
So
yeah.
I was trying to sort of somehow relate this to some mass. It almost looks like it, but
yeah, it almost looks like the New Yao mass, I think, in the expression. But
yeah.
Yeah.
Okay. I was just curious if I was just missing it. It was thank you.
Yeah, thank you for your question. I think this is actually a very interesting direction, but we haven't thought about it in detail yet.
Okay, thank you.
Steven, so the difference H minus the first term that appears here, the trace Q minus Q nu. So this is related to the notion of marginally outshaped surfaces. So people consider this invariant, and so you have this relation to mass.
Yeah,
I cannot really go into it here, but there is something like that. Yes.
Yeah. Okay. Thank you.
Yeah. Okay. Okay. So right. So now let me move on to the next session about initial data set rigidity for convex polytope. Okay. So let me motivate this by scalar curvature rigidity for polytopes. So the first motivation comes from how to define a weak notion of a curvature lower bound. So for example, for sectional curvature, so we can define a weak notion of sectional curvature lower bound by using triangle comparison theorem. So for example, in this direction, when the metric is smooth, then this follows from Gromov theorem. And let's say in the convex direction, when the metric has low regularity, then we can still define a weak notion of sectional curvature lower bound by triangle comparison. So this was used to be the foundation of Alexandra space. Okay. So now the natural question to ask is how about scalar curvature lower bound in lower regularity space? Okay. So this will be a much harder question. Okay, so in 2014, Gromov proposed that we can use polytope comparison to approach this problem. So Gromov proved the following comparison with cube. So suppose M is a cube and G is a Riemannian metric on the cube. Then the following conditions cannot happen simultaneously. So it cannot. So if the scalar curvature is non-negative and the mean curvature is non-negative on the faces, then the dihedral angle cannot be smaller than pi over 2 between the faces. So yeah, maybe let me try to convince you using a 2D picture. So let's say in 2 dimensions, we are considering a square, and then the scalar curvature is the Gauss curvature, and then on the boundary we have geodesic curvature. And if alpha j denotes the dihedral angle between the two edges, then the Gauss-Bonnet theorem gives you this. Okay, And then when these two terms are non-negative, this implies that alpha j less than pi over 2 cannot hold for all dihedral angle alpha j. So this theorem of Gromov motivate the following weak notion of non-negative scalar curvature. So in Rn, so equivalently, we can say that in Rn, if a metric cannot have non-negative scalar curvature, if one cannot deform the faces of a cube to be mean convex while keeping the interior dihedral angle acute. So the picture is a bit like that. So we have like a cube, and if we want to deform a face with positive mean curvature, then such a deformation has to increase the angle. Okay, on other hand, we can say that non-negative scalar curvature in weak sand means that there exists no cube with mean convex face and acute angle for all the dihedral angles. So in general, Gromov proposed the following conjecture. Say we can use, instead of cube, we can also, in general, we can use polytope for comparison. The conjecture says that let M be a polytope and G is a Riemannian metric on the polytope, such that it has non-negative scalar curvature in the interior and non-negative mean curvature on each face of the boundary, and such that the dihedral angle between the faces respect to the metric G is not greater than the dihedral angle with respect to the Euclidean metric. So in this case, the polytope, the metric has to be flat. So the M has to be the flat polytope in Rn. So, okay. So this conjecture about scalar curvature comparison, there are many progresses have been made towards this conjecture. So the first progress was made by Charlie, who used minimal surface technique for dimensions between 3 and 7. Okay, and then once you use Dirac operator method and index theory with corner to attack this conjecture. And more recently, Brendle used Dirac operator method with smoothing techniques to approach this conjecture as well. Okay, so now with so much progress on scalar curvature comparison using polytopes, another question to ask is, going back to initial data set, can we define a weak notion of dominant energy condition using polytope comparison? Okay, so in the Riemannian picture, we have this rigidity statement. So if these three conditions all hold, then M has to reflect. And let's say for the initial data set case, so non-negativity of scalar curvature is replaced by the dominant energy condition. And of course, we will retain this dihedral comparison as well. So the problem comes with how should we impose the boundary condition and how should we replace, generalize this boundary condition to the case of initial data sets. So there are different ways to do that. So our proposal is the following. So we require that the boundary edge, so the mean curvature minus trace norm of the trace of Q restricted on the boundary is non-negative on each face of the polytope. Then the expectation is that in this case, the initial data set associated with the polytope can be isometrically immersed into the Minkowski space with Q being the second fundamental form. Okay, so if this is true, then we can try to define a weak notion of the dominant energy condition. Okay, so let me say a few words about these boundary conditions. So basically, so this difference is closely related to the null expansion. So the null So the null factor is given by H plus or minus the chase of Q restricted on the boundary. So basically, this means that, so if this is true, then this means that one cannot deform the initial data set such that it has more energy. It has larger energy density, and it has more null expansion on the boundary. Okay. And so now the first result in this direction was due to Tsz-Kiu in the dimension 3 for the case of cube. So Zheng used another, so the boundary condition of Zheng is different with the boundary condition of us. So this so in our case, this is this will be the absolute value of the chase of Q restricted on the boundary. So while in Zheng's case, this is the absolute value of the conjugate momentum tensor evaluated on the normal factor nu, and it is called the boundary dominant energy condition by Zheng. So in Zheng's theorem, when M is a three-dimensional cube associated with an initial data set, if all these three conditions are satisfied, then the manifold can be isometrically immersed into the Minkowski space R31, with Q being the second fundamental form. Okay, so Zheng's idea was to use the space-time harmonic function, first introduced by Stern and by Bray, Hurst, Kazawa, Curie, and Zhang. So the first step in Zheng's proof is to first solve the boundary value problem, and the solution of this PDE is called a space-time harmonic function, and then apply the Stern-Butler formula to obtain rigidity. Okay, so let me not go into the detail of his idea. Okay, so now I would like to mention our second main result about polytope comparison for initial data sets. Okay, so this result holds on all dimensions bigger than 2, not at least 2. Okay, so suppose omega GQ is an initial data set such that omega is a compact convex polytope in the Euclidean space Rn. And we assume that the dominant energy condition is satisfied inside omega, and exists at least the chase of Q restricted on the boundary on each phase of the polytope omega. Okay, and the third condition, we assume a matching angle hypothesis. So it is a slightly stronger condition conjectured by Gromov. So the matching angle hypothesis assumes that the dihedral angle with respect to the metric G agree with the dihedral angle with respect to the Euclidean metric. Okay, so this is also the condition used by Brendle in his proof of in his work on scalar curvature comparison. Okay, so under these conditions, then this initial data set can be isometrically immersed as a space-like hypersurface into the Minkowski spacetime, such that Q is the second fundamental form, and each boundary phase of the polytope omega is totally geodesic as a codimension 2 submanifold in the Minkowski spacetime. Okay, so we do have this rigidity statement under these assumptions. Okay, so I don't have too much time, so let me quickly go through the proof idea of this theorem. So basically, we will employ the similar strategy developed by Brendle in his proof of post PSC proof, and adapt this strategy to initial data sets. But the first step is to construct an approximation. So is to approximate the polytope by smooth convex domains. The second step is that on each smooth domain, we solve a perturbed Dirac equation and then apply Weissenberg formula to derive an integral estimate. Okay, and in the final step, together with some a priori estimate, we will pass to limits and derive a a parallel section on the entire polytope. Okay, so in the first step, we can write the polytope as an intersection of sub-level sets of linear functions on Rn. So here Nj denotes the unit normal on each level set of the linear function, and nu j, so Nj denotes the unit normal with respect to the Euclidean metric, and nu j denotes the normal with respect to G. And for lambda to be a large number, we consider a domain omega lambda defined by this formula. So when lambda is large, omega lambda will be a smooth convex domain Rn with smooth boundary. Okay, so this is the picture. So this is the polytope omega, and for lambda R, omega lambda will be a smooth convex domain that approximates omega. And here we will denote nu lambda to be the normal factor with respect to the smooth domain with respect to the metric G. And we also define a map n lambda by this formula so that it has positive degree. Okay, so if we define n lambda this way, then when lambda is large, n lambda will approximate ni, which is the Gauss map on the polytope with respect to the Euclidean metric. And when lambda is large, n lambda is homotopic to the Gauss map on the smooth on the boundary of omega lambda. Okay, so this implies that by convexity, this implies that degree of the map n lambda is positive. Okay, so having constructed this approximation, now let's focus on odd dimensions. Then consider a sequence lambda L to infinity. Then we can apply, so because now on each omega lambda, it is basically a smooth manifold with boundary, we can apply the same argument in theorem A. So find a long-trivial section SL and satisfy this integral estimate coming from the Weisenberg formula. Okay, and we can find a long-trivial section because the degree of the map n lambda is positive. Okay, and the difference between this case with the case in theorem 1, in theorem A, is that in the case of theorem A, this boundary term is a good term. Okay, but in this case, in the polytope case, this is a good term coming from dominant energy condition, but this is not a good term. This is actually a bad term. Okay, so it is not non-positive. This is because that in this case, we only assume that H minus the trace of Q evaluated on the boundary of the polytope is non-negative. Okay, so this term is a bad term. Okay, but what we can do is we can obtain some a priori estimate on this term and to control this bad term. So basically we follow the same strategy of Brendle using a Dick theorem from Pfefferman and Form with these boundary conditions. We can derive the following a priori estimate of the boundary term. Okay, so the boundary term is controlled by O1 times the gradient term plus O1 times the zeroth order term. So here U is basically a fixed Euclidean ball in the polytope omega. And then the integral estimate from the step 2 with the a priori estimate from step 3. So this implies that the integral of the gradient of S L square So the gradient term is bounded above by O1 times the 0 L2 term. Okay. So we can combine these two integral estimates to derive this inequality. And this implies that if we send L to infinity, the right-hand side will go to 0. And again, we can set limits. Okay, so this allows us to pass to limit as L goes to infinity. And this gives us a convergent subsequence, which converts to a limit section S. So here, S is a smooth section on the bundle E over the polytope omega. Okay, so this is a section defined in the interior of the polytope and satisfy this parallel condition. So this is a parallel section together with a boundary condition. And consequently, we can, similar to the proof of main theorem A, we can use this ODE to show that the polytope is isometrically immersed into the Minkowski space as a space-like hypersurface, with Q being the second fundamental form. And the boundary condition. And this boundary condition can also be used to show that S is an invertible section as a matrix, and that will also give us a basis of parallel spinor. Okay, which will then be used to construct this isometric immersion. Okay, and by exploiting the boundary condition with this equation, we can also conclude that each boundary phase is a totally geodesic codimension 2 submanifold in the Minkowski spacetime. So this concludes the proof of main theorem B in odd dimensions. And even dimension, the proof is also similar to the proof of even dimensions in theorem A. So basically, we consider the omega tilde, we consider a product of the polytope with S1 and then one similar argument on this product. Okay, so I think this is all I want to say, and this concludes my talk today. And thank you for listening.